Yeah, good morning, everyone. I'm Kingsley. I'm a civil engineering PhD candidate here at UT Austin. And thank you for taking our time to attend my final defense presentation titled Data-Driven Modeling and Control of Grid Interactive Communities. So the agenda for today is I'll start off by providing the motivation for my work, and then the research questions which we sought to address, as well as the contributions towards addressing those questions. And finally, I'll conclude by showing how we've used our contributions to provide educational material and also for outreach. So historically, the electricity value chain has been unidirectional, where you have the power plant operator that generates electricity from fossil fuel sources as well as renewables. And then the transmission system operator was responsible for transporting that electricity over long distances to the distribution system operator or the utility companies whom the consumers directly interacted with. So the electricity loads at the time have always been cooling loads for space cooling, and then plug loads, especially for the residential sector. However, the face of the market has changed quite a bit in recent times. So for one, there has been the emergence of the prosumer, who pretty much generates electricity on site from renewable sources such as solar PV. And this electricity sometimes will either get sent back to the grid or get stored if there is excess. Secondly, there has also been the electrification of heating end users as well as transportation towards decarbonization. But more importantly is the fact that electricity has become bidirectional. So in cases where there's excess generation, the prosumer could send back electricity to the grid, or in some cases, even if it's not in excess, they could receive credits by providing some electricity generation to the grid. So these changes have their challenges. For one, there has been increased demand. So the peak demand has increased, as well as the overall consumption for electricity, which means there is now the need to provide more power plants to meet this growing demand. And then aside the increase in the magnitude of the peak, the timing of the peak has also shifted. And with large loads like electric vehicles, everyone upstream of this market now has to account for those new peaks in terms of matching supply with the demand. And the reverse power flow also brings about grid instability issues. And lastly, with the intermittency of renewables, even though abundant in some locations, bring about challenges in the sense that we need to be able to ramp up generation at the same rate at which these renewables deplete. And in some cases, that is not always possible, and the effect might be rotating blackouts. So demand response is one way to address some of these challenges, where the utility either sends out a signal or directly controls the customer's assets to increase or decrease their demand. Times when the wholesale electricity pricing is fluctuating, or if there is a mismatch between supplied electricity and the demand, or at critical periods when emergency supply is needed at a certain area. So generally, there are three types of demand response. In price-based demand response, the utility implicitly incentivizes customers to shift their loads from periods of high peaks to periods of low peaks. And these incentives come in the form of, say, a specialized rate, for example, time of use pricing. And then with event-driven demand response, what we have is a more explicit incentivization from the utilities for customers' willingness to allow them control their loads, or possibly for the customers to intervene and provide the grid with some flexibility when there is demand-supply mismatch. And these incentives can come in the form of reduced bills or credits. And then in demand reduction bids, larger customers with larger loads and more flexible loads can pretty much bid into the electricity market to to provide the grid with some flexibility. However, there are issues with demand response. First is the rebound effect, where while you're able to reduce the load during the demand response event, that load only ends up getting shifted, and in some cases ends up getting exacerbated compared to the default if there were no event. So an example could be in the case of increasing the cooling set point so that we could reduce the load. Only for that set point to be reduced even below the defaults to quickly cool the space down after the event. And then demand response is also not occupant-centric. For one, it usually requires some form of human intervention, or at least in the case of price-based, it requires that the customers track the pricing to make sure they maximize their value from those programs. Since it's more of a reactive approach to control, it will often sometimes bring about discomfort. So in the literature, we found that there are usually high rates of overrides of control during demand response, or they're just low adoption rates of demand response programs. So this is why the Grid Interactive Efficient Building Initiative by the Department of Energy is pretty important. So in the definition put forward by the DOE, GEBs optimize for demand flexibility, costs, grid services, and comfort continuously. To begin with, they're already built out of high efficiency envelopes and appliances, so they're able to operate at a much lower demand than buildings that are built to code. And for that reason, you don't have to change the building function for them to work out. And then they're also able to generate their own electricity on site, so further reducing the dependency on the grid. And their most promising feature is their ability to flex their loads to continuously adapt to the changing supply-demand imbalance conditions. So that way, if the demand exceeds the supply, they can pretty much shed their loads. Or if there is benefits in storing electricity in either thermal energy storage or electrical storage, to probably discharge later on when electricity is cheaper or cleaner. However, to unlock this multi-objective nature of GEBs, there is a need for smart controls that can continuously adapt to the current conditions, but also have some form of predictive knowledge of the future when managing these different distributed energy resources. So like this is strictly in contrast to the traditional demand response that is more reactive and doesn't have that predictive ability to plan ahead. So there are generally three control strategies for building energy management. So first being rule-based control, model predictive control, and reinforcement learning control. And we can distinguish these three based on their predictive ability, their constraint handling, ability to find an optimal solution, adaptability to new buildings and new occupants, their computational costs, and the existing barriers for their adoption. So when we look at rule-based control, so this is the most common and more popular control you find in building energy systems. When the designer has a lot of experiential knowledge about the building, they're able to set up really good rules that provide good results. Also, they have little to no computational costs because they're simple if-else statements. Thus, they don't have a lot of, there's no barrier to their adoption. However, there is no explicit definitions of their constraints. They don't provide an optimal solution, no predictive ability, and do not transfer well to new buildings. So if the rules are set, if you can't typically take those rules to a new building, or if a new occupant comes into that building, it might not work as planned. So on the flip side, with model predictive control, as the name implies, it has that predictive ability. The constraints are also explicitly defined. And when the objective function is also well defined, you can get an optimal solution out of it. But like RBC, it is not adaptive. If there are to be a new building or occupants, the model will have to be refit. And the computational costs are high in the sense that there's a computational cost of fitting the models. And then also during inference, when you deploy, there's also a high computational cost. There's also a lot of effort that goes into the actual modeling of the buildings for MPC. So these feed into the barriers preventing the adoption of MPC wide scale. Now, RL, reinforcement learning, on the other hand, is predictive like MPC. While the constraints are not explicitly defined, you can implicitly define them in the reward function, which I'll speak on shortly. You can achieve near optimal solutions, especially as more training data become available. They are adaptive, and unlike MPC that has high costs both during training and also during deployment, with RL, you only incur that cost during the training. But the frequently talked about barrier to adoption for RL is its large data requirements. So I'll quickly just introduce what RL is. So first, it's pretty much a formalization of learning from trial and error, where an agent learns from experience by taking actions in the environment that will maximize its rewards long term. So it starts off by get a pointer. So it starts off by taking the observations from the environment, and then these observations can be things like the indoor temperature, the weather conditions, the current state of charge of the storage devices. And then using those observations, you can then prescribe an action. And this action could be to control, to either charge or discharge the storage. So the action affects the subsequent observations at the next time step. And then the environment sends back a reward that pretty much quantifies the quality of the action that it just took. So what the agent then does is it takes the previous observation, the current one, the reward, and the action to update its knowledge towards taking better actions long term. So this process of learning through interactions is pretty powerful because it means the agent does not need to be aware of the physics of the system it's pretty much controlling. And just by collecting observations and taking actions and receiving those rewards, it can learn to take, good steps towards the defined objective. All right, but there are still barriers to the adoption of RL in the real world. And from the literature, we find these 4 problems. So the first is sample inefficiency. Because RL is dependent on experiences, it will need a lot of training data that is representative of most scenarios to see in the real world. But that is not always possible to get that data. Secondly, being a trial and error approach, there's the risk of taking expensive or unsafe actions, especially during initialization. So things that could lead to discomfort, lead to increased energy bills. It's things that you could experience due to that trial and error approach with RL. And then thirdly is the generalizability. So while it's an adaptive approach, it has a tendency to overfit to the scenario it's trained on. So to solve these problems, we typically need a simulation environment where we can test and train different RL algorithms and also benchmark them against each other. However, the existing state-of-the-art environments either have too high domain knowledge or are lacking in their robustness to control and benchmark diverse loads, especially when you consider the multi-objectivity of providing flexibility, for example, balancing energy efficiency, but also making sure that the occupants remain comfortable. So this brings me to the 3 research questions that this dissertation addresses. The first is we want to formalize the challenges of real-world RL implementation in green interactive buildings and identify how they can be resolved. Secondly, we want to investigate if reinforcement learning can provide occupant-centric control that is tailored to existing grid interactive buildings using data-efficient and scalable technologies. And thirdly, we want to see how we can reduce the entry barrier and complexity of distributed energy resource control benchmarking with a holistic approach that works towards providing energy flexibility. So in the first contribution, we added to the existing literature on real-world RL challenges, but by contextualizing them within the GEB framework. So Dulac et al. Formally introduced these 9 challenges that, if addressed, will accelerate the application of RL in the real world. And these we can classify into infrastructural challenges, safety and trust challenges, and thirdly, data sampling and generalization challenges. So our contribution, as I mentioned earlier, is to contextualize them within the GEB framework, propose an evaluation criteria towards addressing them. I do not go into the details of all 9, because that'll take a long time, but we can revisit them at the end of the talk. But to demonstrate our contextualization in practical terms, we addressed challenge C8, which is training offline from fixed logs of an external behavior policy. So for challenge 6.8, the context for GBs will be to learn a control law from a suboptimal but expert agent, such as role-based control. And the evaluation is then the impact of offline training length. So how long we spend providing data from this expert controller, and also the quality of the expert controller. So pretty much how much experiential knowledge has been put into developing that controller. And then we can see how the learning trajectory for the RL agent changes for these different conditions. So for this work, we made use of the CityLearn V1 environment, which was pretty much designed for benchmarking simple and advanced control algorithms through aggregated load shaping. In CityLearn V1, the building loads are all pre-computed from energy simulation. So for example, Energy Plus. And then the work of the environment is pretty much to accept actions from a controller so that it decides on either discharging or charging stored thermal or electrical energy to satisfy these pre-computed loads. So the environment data sets we use is a 9-building district that comprises of office buildings, service buildings, retail, and also multifamily buildings. And in these data sets, all the buildings have thermal energy storage for cooling. And also they all have electrical storage to offset the electrical load from the grid. And then in most cases, there is thermal energy storage for domestic hot water heating. And in some cases, there is PV to provide on-site generation. So for the RBCs we used for the offline training, we used 2 variations. In the first one, it's been optimized to be more granular by charging the storage systems at a higher rate when it's coolest compared to other periods of the day. So these buildings were set in an Austin, Texas climate zone, which is cooling dominant. So it makes so the most of the loads for the building will be attributed to cooling the spaces. And since we use a heat pump to cool the to provide the cooling energy to the thermal energy storage, and the coefficient of performance for heat pumps improve, at least in the cooling scenario, if the temperature is lower. So it makes more sense to cool to provide the cooling energy at the coolest time of the day. And then on the flip side, we are discharging at a higher rate when we expect the peaks to occur between I think 4 to 6 p.m. And then for the second RBC, regardless of how cool or how warm it is, we're charging at a constant rate. And then we discharge at a constant rate for every other hour, regardless of if it's a peak period or not. So consequently, the optimized RBC, as we can see in this figure down here, provides about 30 to 40% reduction in the average daily peak by providing more experiential knowledge in its design. And then for the RL controller, we made use of the Marlisa algorithm, which is a multi-agent algorithm that coordinates all the buildings in the district to reduce the aggregated load for the district. And how it does that is by each agent pretty much predicts what the anticipated electricity consumption is for the building, and then that's consumption gets shared with all the other agents anonymously, so that you can have an idea of how everyone is acting in the environment and pretty much cooperate towards reducing the overall district load. And for our offline training, we provided logs from either RBC for 1 month or 6 months or 1 year. And then we pretty much trained for the remainder of a 5-year single episode. So in the results shown here, we're showing the average daily peak for the entire district, where we compare the Marlisa agent to the optimized RBC when we use that for the offline training. The dashed line is the value for the black dashed line is the value for the RBC, and the values for the RL has been normalized with respect to the RBC. So pretty much any value that is lower means we're performing better, and values that fall below the dashed line means we're performing better than the RBC. So for this particular result, we see that with just using the optimized RBC, which has a lot of experiential knowledge put into it, we will outperform the reinforcement learning controller. So this pretty much corroborates what we earlier established, that with experiential knowledge put into the design of an RBC, it can perform very well. Now, on the flip side, when we look at using the basic RBC, the polytuned RBC, reinforcement learning will perform either just as good. So in the beginning, we're just on the dash line, or over time will improve on the rules that it has learned from the RBC. So this is important when we consider performance and safe exploration at the time of initialization, because right here we are not performing any worse than this, generic RBC, but over time we have improved the performance. And then when we look at the length of the offline training, so pretty much comparing the different colors, the trajectories, we see that longer offline training on the optimized RBC will result in better RL performance. So that's the green line is 1 year, and we see that we have lower values over the years compared to the others. But the reverse is the case when you try to offline train for too long with a polytuned RBC. So a conservative approach is we want to offline train just long enough to a point where the RL controller is aware of safe actions, but not spend too much time to avoid overfitting to a poorly tuned controller. But then if there's a well-known expert-tuned RBC that has been used for time in the building, it is worthwhile spending more time offline training the RL controller on that controller. So what we've shown so far is empirical evidence that for buildings, the amount of data is not really an issue, since we can take advantage of existing logs. This is important because it's well known that RL tends to be data hungry, but this saying originates from other applications of reinforcement learning, such as robotics and computer games, where there are not well-established rules for control. All right, so the second contribution then sought to answer if we can provide occupant-centric control to existing grid interactive communities. For this contribution, we developed the Merlin framework to provide offline and transfer learning for flexible operation in grid interactive buildings. So starting with the real-world community here, we collect data on the building's loads, weather conditions, emission and electricity pricing rates. And then next, the virtual representation of this community is built in CityLearn, where we can then benchmark simple control like RBC or more advanced control like RL and MPC in controlling the different resources in these communities. And then there's a pre-processing step where we calibrate this simulation environment to make sure that we're operating close enough to the real world community. And then other RL related parameters like the state and action space, the reward function get designed. And in the case of MPC, the control objective gets defined. And then any other thing in terms of like tuning the hyperparameters for these controllers will also occur at this stage. And then we run control simulations for different scenarios and evaluate them against a set of key performance indicators. So things like how well are we reducing the emissions, how well are we reducing the costs or the peaks. And when we finally establish a control law that provides us with the KPI values that we want, we can then take that control policy and deploy it back in the community, and then pretty much evaluate deterministically how we're performing with that finalized control law. So this framework allows us, for one, to test the efficacy of reinforcement learning or any other control approach on real world GB data sets. But as I'll show shortly, we are also able to use it to evaluate how a trained agent will perform when deployed in a building which it wasn't trained on, as is the case with new construction or private data privacy issues. So in our case study, we used a 17-building zero net energy community located in Fontana, California. The buildings are all single family, and just like GBs, they have been built with high efficiency envelopes and also have high efficiency appliances. So they pretty much perform at a level that is above the minimum code requirement. And then these buildings are able to flex their loads using a battery PV system that is controlled using a role-based home energy management system. The data provider, the EPRI Electric Power Research Institute, who was a stakeholder in the community's development, had an objective to take advantage of the storage systems to reduce costs and emissions in the community, which we then framed our case study after. So for our control, our baseline was a scenario where the buildings only had solar generation and no batteries to save any excess generation. So everything else beyond the building's load got sent back to the grid. And then the second control, which pretty much mimics the actual rule-based control in the community, was geared towards reducing the peak loads. So how it worked is in the morning, just when generation was ramping up, self-generation was ramping up, it's charged the batteries at a constant rate and then delayed till later in the evening during the peaks to discharge the batteries at a constant rate again. And then for more advanced controller, which we wanted to use to improve the RBC, is the SAC, soft actor critic. So this particular RL algorithm frequently shows up in literature for building control problems because it works very nicely for large state and action spaces that are also continuous. And in this case, what we did was we offline trained the SAC with the actual RBC for the first 5 months, and then continue training over 10 episodes for a year each. And then for our reward function, we had a weighted reward of costs, so the C, and emissions, G. So pretty much the goal is to maximize our rewards, right? So we also had the penalty term here. You probably call it like a consumption penalty term. And what that penalty term does is it reduces the reward if there is consumption from the grid when the battery is fully charged, or if there is export to the grid when the battery isn't fully charged. So that way we kind of encourage maximum use of generated solar and stored energy. And then we evaluated 2 deployment and training strategies. In the first, an ideal training approach is where the agent pretty much is trained for each building one agent to each building is trained with the actual building data onto a convergence, and then the trade agent is then evaluated deterministically afterwards. And then the second case, we employ transfer learning in one of two ways. In the first, we assume a limited number of buildings are sharing their data. So with a few buildings for which we have data, we train agents and then deploy them in these unseen buildings to see how they perform. And in the second case, we use a limited number of time periods. So instead of using the entire year to train, we only use like 5 months, and then see how the agents transfer, considering that the building loads are seasonal. So when we look at the results for the first deployment strategy, we see that we're able to take better advantage of the solar generation used in charging the batteries, and that results in less consumption from the grid. That's the blue for the RL, compared to the RBC and the baseline case. Consequently, you also drive down the cost and emissions because those are typically tied to also consumption. And then if you look at these other 3 KPIs, so the average daily peak, ramping and load factor, we're also we're able to reduce them beyond what is being provided by the actual RBC and the baseline. This is particularly important because these agents are acting independently. So unlike the Marlisa example in the first contribution, where there's some knowledge being shared amongst the agents, with the SACs, the buildings are doing their own thing with their own agents, but still we can get results that are beneficial to the entire district. But then for zero net energy, we're not doing too well with the RL and neither with the RBC. However, this is in a good way because in the baseline scenario, we were benefiting from the fact that generation was excess. So in the long run, we exported more than we imported. However, the timing was off, that it didn't necessarily translate to cheaper or cleaner electricity. But here with the RL, we are taking better advantage of this excess generation by storing it. And while the battery could definitely increase the consumption from the grid when there's no solar to charge it, the reward function makes sure that it's only doing that when electricity is cheap and when electricity is clean. And then the second figure shows the case when the train policy for one building is transferred to an unseen building. So the orange will be source building that gets transferred to a target building, the black. And then like before, a lower score is better, and markers in the gray shaded region indicate that the transferred policy is performing better than the baseline. And then the red markers are if we had just used the reference RBC to control the batteries, and the green is if we had trained the RL controller using the ideal way where we actually use data from the building. So what we see is that transferred policy will more often than not perform worse than an ideally trained policy, which is expected, right? Because we don't actually use the data from the building, but we're still doing better than the baseline and the RBC in most cases. So this is particularly important because the implication is that we do not need to collect data from all buildings in a neighborhood, assuming there are privacy concerns or there's new construction, thus there isn't meter data yet for a building. You can still take advantage of already trained RL agents in new buildings. The only challenge then becomes identifying which of these orange buildings is a closest match to the target building. So there is active research in this area to pretty much identify the appropriate distance metrics and also the features for those distance metrics that best quantify similarities in buildings during transfer learning. And then finally, just focusing on the load shapes, this figure pretty much shows how the RBC is, for one, creating a new peak and shifted peak on the average day. So this red line is the RBC, and we can see that compared to the dashed black line, which had a peak later in the day, here we're having the peak shifted to an earlier period. But then when we compare it to the RL, for one, it has adapted to the unique load profiles for all the buildings, which pretty much implies that it's adapting to the different occupant behaviors that drive these load profiles. But it's also able to reduce the building and district peaks and also flatten the load shape by shifting the loads. So far, we've established that we're able to provide safer reinforcement learning with offline learning from a rule-based controller, and that RL will improve building and grid level KPIs over existing real-world control strategies. And that transfer learning can provide scalable RL deployment. So in our third and final contribution, we developed an extended version of CityLearn to address some of the limitations that exist in state-of-the-art environments for control benchmarking have. So in the first release of CityLearn back in 2019, there was one limitation, which was its ability to model the building's thermodynamics. So if you remember in the first contribution, I mentioned that we use pre-simulated building loads. So that is the reason we didn't have a way to pretty much quantify how the temperature in the buildings would change if those thermal loads changed. Also, there wasn't a way to generate customized environments. So like a user was restricted to just the buildings and resources that came in the installed version of CityLearn. And then other features to help further quantify energy flexibility and its implications, such as loads from electric vehicles and also how occupant interactions affect flexibility, were not modeled in that initial release. So over the years, there have been other control benchmarking emulators that have addressed some of these challenges. For one, the thermodynamics has been modeled using physics approaches or reduced order models. But also, there have been applications of large building stock data sets like the end-use load profiles by OCHRE to, provide customizable environments. And then a few of them have also had EV loads modeled in them. However, things like occupants, interaction modeling, and also resilience modeling to be able to evaluate these controllers based on how they would perform in, say, the power outage, have not been considered. So with the CityLearn V2 environment that we developed with the help of a lot of other researchers, pretty much what we've done is we've included a data-driven thermodynamics model that uses long short-term memory neural networks to encode the temperature evolution in the building, which then means we're able to control the heat pumps, which affects the thermal loads, and we can tell how the temperature in the buildings will change. So this is based on the work by Pinto et al. And then secondly, we developed a framework that allows us to generate representative neighborhoods of any county in the United States, single family, giving a set of metadata filters. Just like with OCHRE, we're taking advantage of the end-use load profiles data set to generate these different environments that we can then plug into CityLearn to carry out control studies. And then based on the work by Fonseca et al., we've also included an electric vehicle module to provide more realistic representation of the loads for the future. And then a dynamic occupant feedback model that uses logistic regression and decision trees to pretty much decide if an occupant will interact with their thermostats given the current temperatures of the building and by what degree they will change the set point, was also included in this version based on the work by Casper et al. And lastly, we developed a stochastic power outage resilience model to be able to assess pretty much the control algorithms performance during blackouts. I do not go into detail how all these models work, but again, we can also revisit this at the end. What I speak more about is how we are generating these single family communities. So using the end-use load profiles data sets, we're able to pretty much specify different building metadata criteria for which we want to see in these neighborhoods. So it can be things like the construction year what kind of installations we want to include, and also a county to define the location and the number of buildings we want to see in the neighborhood. And then we use a cluster-based frequency sampling to transform the metadata to numerical values and then apply k-means to pretty much identify different groups of buildings that have similarities based on this metadata that we are considering. And then we can pretty much from those different building groups randomly select a certified specific number of buildings. And then the next step is to collect other data, such as whether the building schedules in terms of when the occupants are turning on and off their plug loads, and also the schedule for water use. And optionally, you can also take advantage of data sets like Ecobee to provide more realistic thermostat set point profiles. Then the next phase is where we carry out energy plus simulations to generate the plug loads for the buildings, but also the domestic horizontal loads. Then on top of that, we're also running a number of simulations to generate data that we can then use to train our LSTM models for the thermodynamics. And then anything concerning resource sizing and what distributed energy resources are included in the community get decided at this point as well. And then finally, we can take the generated data sets from this point and plug it into CityLearn after we've pretty much designed our control algorithm and carry out any control studies like we did in the second contribution. So as you can see here, with a few lines of Python code, we have been able to pretty much automate all the steps that precede the actual control simulation. So we can pretty much take advantage of the over 300,000 residential building models that the end-use load profile provides us with to carry out holistic studies on control in grid interactive communities. When we look at some of the preliminary results from 3 neighborhoods that we generated with this V2 environment, we see that the load shaping brought about a battery PV system in these neighborhoods using reinforcement learning pretty much shows that we get different results, even though we had followed the same approach in terms of how we sized the batteries. So for this, what we did is we sized the batteries and PV to work for a zero net energy case. Yet we see that we end up with different levels of flexibility. So if we take Travis County, for example, which is pretty much Austin, we see that we're able to flatten the load a little bit better and also reduce the peaks. But that comes from the fact that we are able to maximize our utilization of the battery. So as you can see, we charge up to 100% state of charge and also discharge down to 0. Now, on the flip side, when we look at, so by the way, for Travis County, we're evaluating just the summer. On the flip side, when we look at these other 2 locations, which are for Chittenden is much cooler, and for Alameda, it's somewhere in between Travis and Chittenden in terms of how cold it gets. We see that for Alameda, we're also taking, for the most part, full advantage of the resources that we have. And to some degree, we are reducing the evening peak, but there's a morning peak, as you can see here, that we are not quite reducing, even though we are pretty much using the same control approach in these three locations and it's the same DER sizing approach. And if then the batteries are barely being used. So we end up with just pretty much the same profile as the baseline. So when we look at the figure on the right, it's pretty much a translation of what we see in these profiles, right? So we are able to minimize these different KPIs the most when we consider Travis County compared to the others. And then for Chittenden, which is performing worst, we're just as good as the baseline of slightly 2% better than the baseline. Okay, cool. So at this point, I would like to conclude my presentation with the following points. So the work that we've presented in this dissertation shows how experts, RBCs can help in jumpstarting RL to provide safe exploration. Thus, we pretty much reduce the trust and safety concerns of RL. However, as we saw in the first contribution, a well-tuned RBC can in fact outperform RL. So the quality of the RBC will determine the extent to which an advanced control approach like RL will provide any advantages. But where RL really shines is in its adaptive nature compared to RBC, as we saw in the Merlin application. With RL, we can pretty much adapt to unique occupant behaviors and schedules that pretty much influence the building loads. But then in the case of data sharing concerns or the construction of new buildings, we saw that transfer learning from a trained policy in one building to an unseen building will still perform better than the baseline, where we had no flexibility, but also perform better than the existing RBC in the community. But again, to the extent to which we can provide multi-objective flexibility will be constrained by a few factors such as climatic conditions and also different occupant behaviors. And the CityLand V2 environment we have developed so far is purposely built to investigate the impact of these different climate and occupant behaviors on flexibility. So we were able to publish all the work we've shown here so far. So on the left is the papers which I first authored. I was the first author on. And then the ones on the right are the ones I got an opportunity to collaborate with other researchers, which I would argue sometimes is more rewarding than working on this stuff by myself. And then we've also been fortunate to have our work recognized over the years through a conference paper award, a poster award, a hackathon award, and a few travel grants that enabled us to present our work in different locations. And then I would like to end by talking about how we've used the contributions for outreach and education purposes. So over the past 2-3 years, we've hosted 2 editions of the CityLand Challenge, which is pretty much a competition that we host annually where we pose a control problem and a multidisciplinary audience, including like researchers, professionals, AI hobbyists, sustainability enthusiasts, provide solutions to these problems. So it's pretty much a nice avenue to crowdsource different solutions to control problems, and these solutions are publicly available. So as you can see, like last year we had up to, that's like 700 people sign up and split into over 100 teams. Similarly, in 2023 and 2022, pretty much the same, about the same number of signups. And then we've also had an opportunity to create educational material for the Climate Change AI Summer School in 2023 and 2024, where we pretty much designed a Jupyter notebook that walks through how to set up an RL control problem for green interactive buildings, with also exercises at the end. And then more recently is the occupant-centric green interactive buildings course, taught for the first time in spring of 2024 here at UT, led by Zoltan, where I pretty much introduced the students to everything pretty much green interactive buildings, but also at the end, we provided them with the CityLand Challenge 2023 as their class project. And we got really great feedback from the students. So that brings me to the end of my talk. I'd like to say thank you to everyone, most especially the committee members, and even more especially Zoltan, who has figuratively held my hand over the years, teaching me how to do good research and just be a better person all around. And also thank you to everyone from utilities and energy management whom I've worked with over the years and have been really supportive of my work, and all my lab members, past and present, and all co-authors whom without them, there'll be nothing to present. And finally, thank you to my family for their support. The end. Thanks.
Okay.
Okay.
So you can just turn around. So
Okay.
we can see. So first, I would like to ask audience, non-committee members, to come up with questions. And Zoltan, I think you can manage. I think you're master of the remote. So questions. And again, thank you for
I'm shy. Now it's the time to speak out.
So I think most of the audience is
It's like a classroom. No questions after
So,
lecture.
it's to COVID teaching. Yeah.
Yeah. Well, okay. Oh, there's one. Muhammad. Can you unmute and maybe show your mic, your video? There you go.
Hi, Kingsley. Can you hear me?
Yes, sir. Yeah. Hi, Mohammed.
Very nice presentation. Congrats on the great work.
Thank you.
I have a question from slide, if I can pull it up, where was it? Slide 46, actually.
This one?
Yes. So maybe this was a bit like not clear to me, but I was curious, the ramping KPI, how do you see this like KPI, let's say, affecting the control policy learning? Like, is it the ramping, does the ramping of the load help in like finding out whether the grid would be able to provide the active power that is needed, or like what's could you like elaborate the value of this KPI specifically? Because I understand load factor is a good one because it reduces the peak demand, or let's say, yeah, but ramping was a bit unclear to me.
Yeah, so the way we calculate the ramping is the difference between any two consecutive loads, right? And the idea is we want to reduce that difference because what it implies is there is a much more gentle increase in demand, which then means the fact that renewables are intermittent isn't as much an issue because we don't need to pretty much power up these fossil fueled generators at a much faster rate to account for that steep climb. So in that,
Right.
we want the controller to be able to provide a policy that has a much more gentle increase in that load over time. Yeah.
Yeah, right. Because this was more from power system perspective that whenever we have like transformer downstream, normally the LV side, there is enough active power unless there is a voltage issue. So, but I mean, this is more of a power flow question, but that's already a nice answer. And I was just curious also about computational complexity that you had for like various results of MARL and like the Merlin and also the sorry, what was the name again? But yeah, I was just wondering what's the computational cost that you had for training all of these algorithms?
Yeah. So for Merlin, we took advantage of the TAC supercomputers here at UT. And I think I was training for 10 episodes per instance, and I was doing it in parallel. I think it took me probably, I don't want to say no, but I can't remember. This was like 2 years ago, but probably under an hour to do the training,
Right.
something like that.
So quite efficient then. Yeah.
Go ahead.
Quite efficient, I would say.
Yeah, but we're using TAC computers, supercomputers, so there's that context. Running
That's true, yeah.
my computer, I don't think it gets I don't think it's too much worse than that, But what happens is that I can't run as many jobs in parallel as I can on TAC. But in terms of like the length of the training, the time for the training doesn't really change. It's just TAC has much more nodes, so you can run 1,000 things at the same time.
Sounds good. Thanks a lot.
Of course, thanks.
Next question from audience.
I have a question.
Go.
Hi, Kingsley. Great job. I have a few questions actually. One, I should know the answer to this, but could you remind me why for that one study where Chittenden, Vermont didn't perform as well as the other communities, like what were some of the hypotheses as to like why we weren't seeing as much impact in that region, and like how would you rectify that, I guess, if you're looking to replicate in other areas?
Yeah, so in this, I think I mentioned in the Merlin like framework, there is some hyperparameter tuning that we did for that particular location, right? So here we just assumed the same starting point for all the buildings, irrespective of location. So that is one thing that definitely provides some value if you spend some time, because these RL is a machine learning approach, and with machine learning algorithms, there are hyperparameters that the model will be sensitive to pretty much. So here we didn't do that. But that's pretty much the point of this study, right? We wanted to show that with the same initial conditions, it will not always transfer nicely to different locations. And then with Chittenden, from a climatic perspective, compared to, say, Travis County, where Austin, that is always very hot and you have a lot of sunlight, you don't necessarily have that in this particular location. So that would affect how much flexibility we can provide from to charge the batteries with solar, pretty much. Yeah.
Okay. Oh yeah, that makes sense. And I have a second question that's kind of along the same lines. I find, at least with my research, sometimes you get to the finish line and then you look back and you're like, okay, now that I know what I know, I would have kind of approached this in a slightly different way. And I guess that's just part of it. But I'm curious for you, like coming to the end now, looking back, is there anything that now knowing what you know, that you would be like, okay, if I were to do this study again, I would do this like differently now?
Yeah, that's a very good question. I mean, hard question. But yeah, I think so. While we focus a lot on RL and more from like an applications perspective, and again, RL is adaptive, right? But I feel like to some degree, you still end up needing a lot of domain knowledge to, say, set up your reward function. You can't just blindly, use something simple like, say, just electricity consumption. It won't always work out nicely, especially as you have more things you're controlling and there's more diversity in the environment. It becomes harder to just have a good starting point. So this is more from like the computer science domain, where they try to like pretty much reverse engineer the reward function, right? As opposed to like how we're doing it, where we're like spending a lot of time, trying out different equations that will provide us with a good reward. So I think that's one thing if I were to do it all over again, I'll probably spend more time in the beginning, coming up with a way to better define those reward functions that will be less dependent on domain knowledge and more dependent on algorithms that can reverse engineer those functions. Yeah.
Cool. That's all. Great job.
Thanks, Catherine. And thanks for all your contribution to all of this we presented here. So yeah.
Next question from audience. Anybody? Okay, once, twice. I think then we can close the questions from audience. Again, thank you everybody for pretty much attending this presentation and also for great questions. Again, I think we are going to now switch to the closed section when only the PhD committee members and the candidates stays in the room. Again, thank you for attending this. I would like to ask you to check out and also whoever controls the recording to stop recording. Pretty much, yeah.
Right.
Thanks.
Thanks, everyone.
Thank
Yeah,
you.
you'll catch him later on.